Today we look at section 11.3, at least the first part in this lesson, in this video. We've looked at two operations so far with vectors. We've added them, and we've also multiplied a vector by a scalar. That was pretty straightforward. We're going to look at a couple more, and today we focus on what's called the dot product. The dot product, notice, yields a scalar rather than a vector. So you take a vector dot another vector, which here's how to do it, and I'll show you that in just a minute. And you get just a scalar. You get a number. Whether it's in 2 space or 3 space, the same thing. Here's some properties of that. I get u dot v equals v dot u. Commutative property does work. The distributive property also applies. You can see all these. There's nothing really surprising here. The dot product of a vector with itself is equal to the magnitude squared. So that's kind of an interesting thing. So let's go back up here. What is the dot product? Well, we simply take the first component of each vector, multiply them, and then add the second component, or multiply the second component and add that together with what we came up with before. So u1 v1 plus u2 times v2. And in 3 space, it's just one more. So it's not too tough. Let's take a peek. First, I've got 3 vectors up here. They're in component form. You'll notice that that's a vector. It's bold print, and it's also got the instead of parentheses, it's got this vector notation. So be aware of that. But anyway, we're going to take a look at these 4 operations, or we may do 2 or 3 of them. I'm not sure which. So let's take u dot v. And that's how we say it, u dot v. And first we'll say that's equal to, so we take 2 times 5 is 10, plus negative 2 times 8 is negative 16, and that's simply equal to negative 6. Straightforward, easy peasy. The next one we look at, u dot v and then times w. Remember, this is going to give me a scalar. So u dot v, which I already did, so let's just go ahead and keep that. That's 6 times the vector w, which is negative 4, 3. And that's equal to 24. It's a vector. So it's 24 and negative 18. There we go. Okay, scrolling down, I've got u dot 2 times v. So we do that 2 times v first. So u is going to be 2, negative 2. I'm going to take the dot product of that with 2 times v, which would be 10, 16. I'm going to let you do the rest of that one. 10, 16. And just remember, take the first coordinates times each other and the second ones and then add them together. See what you come up with. And finally, the third one, the magnitude of w squared, which is equal to, well, magnitude of w would be negative 4 squared is 16 plus 3 squared is 9. Square root of 25 is 5. Now you might want to go ahead and try this, see what you come up with. Excuse me. We still got to square that. Square that, so that's 25. Alright. And you may want to take what is w dot w and see what you get. Alright. Moving along. I've got 2 vectors here, u and v, and some angle between them called theta. And you can see here's vector v minus u as well. But what's interesting here is that if theta is the angle between 2 non-zero vectors u and v, then the cosine of theta is equal to the dot product divided by the magnitude of u times the magnitude of v. You can see this is going to be a scalar number because all of these give you scalars. Okay. If the angle between the 2 vectors is known, rewriting theorem 11.5 in the form of u dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta. It gives us an alternate form that we like, and so if we knew what theta was, we can go ahead and use that one. produces that alternate way to come up with the dot product. Okay. So before we do actually a couple of those, a couple more things to notice. If you can see that magnitude of u and magnitude of v is always positive. So if I sneak back a slide, if this is always positive, the dot product will also, if that's positive, okay, then the cosine of theta has to be positive. And if this is negative, this also has to be negative. So that's what this next slide basically says. If theta is pi, the cosine of theta is going to be -1, which means I've got b, a vector going this way, u, a vector going that way. They're opposites of each other. In fact, they're parallel to each other because one is just the opposite of the other one. All right. If u dot v is less than 0, that means the cosine has to be negative, and the cosine is negative in the second quadrant. So pi over 2, theta is between pi over 2 and pi. If the dot product is 0, cosine of pi over 2 is 0, so theta must be pi over 2, which means that now I recognize something, and that's what I've got right down here. The vectors u and v are orthogonal, or perpendicular, if u dot v is equal to 0. The reason we say orthogonal is just a little bit stronger, especially when we consider when we're in 3 space, what it means to be perpendicular versus orthogonal. Very similar. All right. And now I've got u dot v is greater than 0, which means that the cosine of theta is between 0 and 1. Theta must be a value between 0 and pi over 2. And if the cosine of 0 is 1, cosine of theta is 1, then theta must be 0. So those are some things to watch out for or keep an eye on. So here, let's do, I think I'll just do one of these. If I've got u, v, w, and z, all 4 of these vectors, and I want to find the angle between them. So I'm just going to do letter A, you can do B and C. So if I want to know the angle, let's go back a couple slides, make sure you remember what we're looking at. The cosine of theta is equal to u dot v over the magnitude of u times the magnitude of v. So cosine of theta is equal to u dot v divided by the magnitude of u times the magnitude of v. And u dot v, it's going to be, and I'm going to go ahead and do that out here, I'm going to get -12 plus -1 times 0 is 0. 2 times 2 is 4, so plus 4. Okay. The magnitude of u is the square root of, and I'm going to try to do this part in my head, 3 squared is 9, 1 squared is 1, -1 squared is 1, so I'm up to 10. 2 squared is 4, so that's the square root of 14. Times the square root of, that would be 16, and 4 is 20. So that is equal to -8 over the square root of 280. So cosine of theta is equal to that. Theta then is equal to the inverse cosine, or the arc cosine, of -8 over the square root of 280. And that answer, according to my work earlier, is 118.56 degrees. And you may give that in degrees. It may be asked for that in radians. Just be aware and set your calculator accordingly. Unless you know that answer in your head, but I certainly don't. Okay, you can do B and C here by yourself. I'm sure you can handle that. All right. In space, it is convenient to measure the direction in terms of the angles between the non-zero vectors. I don't know if you can see this real well. I'm going to try to boost that up a little bit so you can see it a little better. There we go. So I've got alpha is the angle between the unit vector I and V. Beta is the angle between the unit vector J and V. And gamma, this other one is called gamma, is the vector between K and V. So we're going to take a peek at those. These are called direction angles. And you can imagine why I want to know what angle it went off from a certain wall or a certain, something or other in a practical application. All right. The angles alpha, beta, and gamma are the direction angles of V, and cosine alpha, cosine beta, and cosine gamma are the direction cosines. So just pay attention to what you're being asked for. If you want to know what the angle is, there it is. If you want to know what the cosine is, there it is. And if we look through this, we've got V dot I is equal to the magnitude of V times the magnitude of I times the cosine of alpha. Well, the magnitude of I we know is always going to be 1. And so it's simply equal to V, the magnitude of V cosine alpha. And we see that here. It follows then that the cosine of alpha can simply be found by taking V1 divided by the magnitude of that vector V. And by similar reasonings, we can see the same thing for cosine beta and cosine gamma. Consequently, any non-zero vector V in space has the normalized form V. So this would be that normalized form. We're looking at kind of a unit vector. Well, we're looking at normalized form. Let me say it that way. Yeah, this should be unit vector. Is V1 divided by the magnitude of V times I, and so forth with each of these. Cosine alpha I plus cosine beta J plus cosine gamma K. Kind of a cool thing to be able to write that way, because this is a unit vector. It follows that all of this squared, each of these squared, is equal to 1. Okay. So let's try to find direction angles here. So I've got a vector 2, 3, 4 coming out right here. You can see the picture of what's going on. And we want to show that cosine, find the direction, cosines, and the angles for this vector, and then show that this is equal to 1. Alright, for time's sake, we're probably going to just do part of this. We've got, we'll find the direction cosines here first. So if I take a peek at that, we've got the cosine of alpha is equal to, well, I'm going to take the I component there, which is 2, over, I need the magnitude of V. Well, the magnitude is going to be 2 squared plus 3 squared plus 4 squared. That's 4 plus 9 is 13 plus 16 is the square root of 29. So it goes here. So that's the cosine of alpha. The cosine of beta, not hard once you get the first one, is equal to 3 over the square root of 29. And the cosine of gamma, that's bad. Let me do that again. Cosine of gamma is equal to 4 over the square root of 29. Alright. If I wanted to find alpha, I would just say it's the inverse cosine of 2 over the square root of 29. And you can do the rest of them the same way. I'll let you do that on your own. And finally it says show that cosine alpha squared plus cosine beta squared plus cosine gamma squared is equal to 1. Let's go ahead and do that. Cosine alpha is 2 over the square root of 29. So if I square that, and you can see what's going to happen here, I'm just running out of time. So that works out to be 4 over 29. Plus, if I square the next one, I get 9 over 29. And finally, the third one, I get 16 over 29. I'll do that math, and that is 13 plus 16 is 29 29ths, which is 1. So we've shown that that's true. All right, we'll pick up with the next one, our next part on the next lesson.